Here's the last question on the assessment. This is a more advanced torsional equilibrium problem. And that's just simply because we've got to read the problem and we've got masses and things like that. Okay, so we're going to torque about this point, right? We've got a 12-meter long beam, all right? So the center of 12 meters is 6 meters, right? The center of gravity will be at 6 meters. That's 82 kilograms. So we've got 82 kilograms. This distance is 12 meters, right? And so what we're going to do is we're going to say that the force of gravity on this guy, this 82 times 9.81, right? I'm going to write it 82G, right, is at 6 meters, right? And that would be half of 12, right? So I'm just going to go through one by one and figure these out, right? So remember, if it's a uniform beam, they use that language there, or even if they just don't tell you, but it looks uniform, right? Then we just say that the center of gravity is at the center of the beam, right? We've got box A is 3 meters from the left side, and it's 25 kilograms. So we've got 25 times 9.8, 1. That's what this is, right? Those are not grams. I mean 25 times 9.81, right? And that is at 3 meters from the left side. So I'm figuring out how far these forces are from that pivot point there, right? Then we've got 937 newtons, that's this guy, is attached some distance. We just don't know what it is, right? That's what we got to figure out, right? Some distance from the left side, right? Then we've got 15 kilograms, half a meter from the right side. That won't do, but we'll figure this out, right? So we've got 15 times 9.81 at 11.5 meters. Okay, and those are all our forces. We've got A, we've got the weight of the beam, which is at the center of the beam. A is at 3 meters because we're told that. B is 0.5 from the right side. Since it's a 12-meter long beam, that makes it 11.5 from the left side. And then we've got 937 newtons at R distance, right? You know, we don't know what the R is, right? But we are going to find it out. Okay. Now remember, for torque, if it's a clockwise torque, we make it positive, right? Torque being R times F, right? And if it's an anti-clockwise torque, then we make it negative. So this guy is going to be anti-clockwise, the tension in that cable. This guy will be clockwise. All of these downward forces will be clockwise. That's positive. This guy's also going to be clockwise, right? And the way you figure that out is you just think about that pivot point. A downward force on any side, on the right side of that, will tend to make this beam rotate clockwise. An upward force about that point will tend to make it rotate anti-clockwise. Okay, so let's just set up our torque expression here. Left to right, we've got some force being exerted at the hinge, but that doesn't matter. Okay, so now we have, we've got at 3 meters, we've got 25 times 9.81, right? At 6 meters, so plus, and these are plus because they're clockwise, right? Clockwise. So plus 6 times 82 times 9.81, right? Okay, then we see, oh, now we got this guy. So minus R times 937, right? And then we have this guy here. So that's anti-clockwise. And then we've got the final torque is this guy. So plus 11.5 times 15 times 9.81. And that's got to equal 0. Now, of course, we can solve that for, I guess, R. There will always be something, right? And the way to do that is just go this times this times this, plus this times this times this, plus this times this times this, add that all together, divide by 937. All right, here we go. 3 times 25 times 9.81 plus 6 times 82 times 9.81 plus 11.5 times 15 times 9.81 is 7254.495, and I'm going to divide by 937. 7.74. 74225 or something like that, right? All right. There you go. All right. Enjoy that. Hope that helps.